Okay, this is part 2. We have only 40 pages. So this is for the orbital physics, and you may notice that there are more and more sessions in the Intermag, MMM, a big conference about the orbital Hall effect, orbital torque, and orbitronics. So here in this part, I would like to persuade you that it is there. This phenomena indeed exists. We don't know how big it is, and we don't know how we can use it. But theoretically and also with a very solid physics argument, this orbital effect exists there. Okay? So I will begin with the orbital Rashba effect. That is actually the appearance of the spin Rashba, which has been widely studied in our community. Then I will introduce orbital texture. So if you want to have only one take-home message from my talk, that is this one. So if you understand what the orbital angular position texture is, then that's enough, because that is the origin of orbital Hall effect, orbital torque, and orbital pumping. Okay, so we have enjoyed spin-orbit torque study for last, I think, 10 years. So typical structure is ferroband metal bilayer. There were two theoretical proposals. One is that this spin-orbit torque arises from the bulk spin-orbit effect of the heavy metal, such as platinum. But the theoreticians did not agree with that. Many things arises at the interface. So this interface effect is characterized by the Rashba effect. A simple picture of the Rashba effect is this one. You have heterostructures. For example, in this heterostructure, there is two-dimensional electron gas. And because you have two different materials, there are some this kind of potential gradient. And because of this gradient, you have electric dipole here. Then it gives this Rashba Hamiltonian. And actually, this is a spin-orbit interaction, and therefore you have to compare it to the original spin-orbit interaction by Dirac, that is the relativistic correction. And then it is given by sigma, spin, p, crystal momentum, and the gradient of the potential. That is kind of a crystal field potential gradient within the solid. Okay? So now, because you break the symmetry along the z direction, this gradient v, it becomes special along the z direction. So now you replace this one to z, and all other parameters enters to this parameter alpha sub r, which is called the Rashba strength. So if you apply the magnetic electric field along the x direction, then your p has non-zero value of x component, and x cross z gives the y, and therefore your spin tends to be aligned along the y direction, which gives the Edelstein effect. This Rashba effect has been known quite some time. However, more than 10 years ago, there was some very important mystery about the Rashba strength. In this paper, they did experiment, they also showed this table. And you see the various element and the number of this Rashba strength ranging from 0.03 to even 3, okay? In this unit, electron volt angstrom. So we can estimate that by comparing the Rashba Hamiltonian and Dirac's spin-orbit interaction Hamiltonian, then this alpha r must be this term universal constant multiplied by gradient of the potential, electric field potential in the solid. And this is known, and this can be reasonably approximated with the work function difference between two materials divided by atomic spacing. Then you will arrive at 10⁻⁴ electron volt angstrom. So when you compare this one, then there are 4 orders of magnitude different. If theory predict 1 order difference, okay, that's theory. 4 orders of different, meaning that this is completely wrong interpretation. So another thing is that when you look at this element in the periodic table, actually there is an approximate tendency that if you use the heavy element, then this alpha R becomes larger. So which means that atomic spin-orbit coupling is important in the Rashba strength. But in this description, there is no atomic spin-orbit coupling. So this interpretation first cannot explain the magnitude by 4 orders magnitude, and it cannot explain the trend depending on the atomic spin-orbit coupling. So actually, in this very nice paper, they suggested that the spin Rashba effect originates from the orbital Rashba effect, and the energy scale is not the thing that I have shown before, but it is electrical energy, which is much, much larger than previous interpretation. So here I have very simplified model. I have 1-dimensional atomic chain, and each atom I have 1 electron, and this electron rotates around this atom. So I can define L, which comes from the R cos P, and when you turn on the spin-orbit coupling, then you can define also S. I take 2 of them here, and this number describes the phase of the electron wave function. Electron is wave function, and therefore there is always phase, e to the I something, that phase. That phase can be described by some number in the unit of degree. So let me assume this here phase 0, here plus 10 degree, here minus 10 degree. So I have next atom, and because here 0 degree, so this is 180, 70, 90. Then you can calculate the phase difference in this interatomic region. So here that is the 160 difference, 180, and 200. And the electron density is square of the wave function. So this is sine square minus 20, and 0, and sine square plus 20. Then you can find that this and that are the same. So in the interatomic space, you have some electron density here, and you have some electron density there because of this phase difference, but they are symmetric. Okay? There is no dipole if you do not consider the Bloch state. So this description is actually wrong because we know that electron forms the Bloch state in the periodic potential. Bloch state means that if you move from one atomic lattice to the next one, there is additional phase of the electron wave function that is given by k times a, where a is the lattice constant. So I assume this is corresponding to the 5 degree. So now this is the same, but I add 5 degree for all phases. Then I do the same calculation. Phase difference 165, 185, 205. So that gives this number. Now you see that you have less electron density here, and you have more electron density there. Now you have electric dipole. Okay? Actually, in this paper, they calculated this electron density accumulation of electric dipole around 2 atoms. So here you see that when L is plus 1, the electron density below the atomic plane is larger, but when you reverse the sign of Lx, then it is reversed. So it is always there because Bloch theorem is always true for any kind of solid. However, when you have this atomic plane within one type of solid, the energy of this configuration and that configuration are the same because environment is the same. Then it does not generate any Hamiltonian term for the electron. However, if this atomic plane is located at the interface between material A and material B, then this part and that part have different electrical environment, meaning that there is a difference in terms of the energy, electrical energy. And this energy is given by this equation. Because it changes the sign depending on L, so how it rotates, L must appear. And actually this difference comes from the Bloch theorem, meaning that you have K, and the energy is different because I break the inversion symmetry along that direction, so you have to multiply inversion symmetry breaking factor. So that is L cross K dot Z, okay? That gives the orbital texture and this system. But still, I don't have spin-Rashba effect because I do not consider spin-orbit coupling yet. Then let me turn on the spin-orbit coupling, and the spin-orbit coupling is strong enough, then your spin direction tends to be aligned along the L direction, depending on the sign of the spin-orbit coupling. Then you will see that the spin-orbit coupling strength, atomic spin-orbit coupling constant appears in the coefficient, and L is changed with S, or S cross K dot Z. This is the Rashba Newtonian. So spin Rashba comes from this scenario. So it comes from the actually electric dipole at the interface. So this is previous estimation, which was wrong, 10 to minus 4. But now, the new interpretation is orbital induced electric dipole plus atomic spin-orbit coupling. The rough estimation is delta E is proportional to electric dipole energy. Relevant length scale is Armstrong. And you just multiply spin-orbit coupling. For platinum, it's about 0.1 eV. Bismuth, it can be larger than 1 eV and so on. Then you get 0.1 to 1 eV angstrom in agreement with the experimental result. Okay, and also it explains why experimentally spin Rashba constant increases with increasing the atomic number because it is related to the atomic spin-orbit coupling. So actually in another paper, they measured Rashba splitting using the angle-resolved photon emission experiment. So they first did without oxygen layer, they got this result. There is almost no splitting, but when they add one oxygen layer on top of the gadolinium, they got this result. And difference between the red and black, so spin up and spin down, is summarized here. Then you see this kind of almost linear in K Rashba splitting. And then you see that it's about, so in number-wise, it's 0.5 eV angstrom, which is large, which cannot be explained by the previous wrong interpretation. So this is the ab initio calculation for cobalt platinum, widely used as standard bilayer for spin-orbit Toc study. And Rashba splitting there, it's about 1 eV angstrom, which is very large. So in collaboration with Aurelian Manchon, we have calculated the Rashba, these various cobalt heavy metal bilayers for various 4D 5D elements, and we calculate the Rashba splitting. And here A is kind of estimate of the Rashba splitting, this one. And there is a charge transfer, meaning that the electric dipole formation, the red one, they follow more or less the qualitatively similar trend. And this is the Rashba strength, blue one. And the red one is the orbital moment at the interface. They also follow more or less the same. So this is all orbital physics, okay? Even though we just use the spin Rashba effect, but actually it comes from the orbital. And there are many more experiments about that. One example was done by our education chair, Hyun-Soo. So in this experiment, they did some strange, they fabricate strange sample, to my view. So this platinum cobalt boron angio, this is kind of standard structure, studied many times, but they deposited silicon oxide on top of it, and they varied the thickness of the silicon oxide, and then they did the current-induced switching, spin-orbit Toc switching measurement. When there is no silicon oxide or thin, then it shows counterclockwise switching, but when it is thick, it is clockwise switching. So spin-orbit Toc sign changes depending on the thickness of the silicon oxide. And after many material analysis characterization, what we found is that actually 2 nanometer MgO is not thick enough to prevent oxygen. So if there is thin or no silicon oxide, oxygen can penetrate MgO and oxidize the copper boron, and it changes the sign. If it is thick enough, then we return to our original understanding about the spin orbital. Okay, and also it relates to the orbital moment to spin moment ratio measured by the XMCD and so on. This is related to the orbital spin. Okay, so we have a Rashba Hamiltonian at any kind of interface. Then we can predict several interesting consequences. So here my Hamiltonian, so very simple one, kinetic, Rashba, SD exchange, and impurity. And here what we have done, we did unitary transformation, theoretical language, but you just rotate local axis in order to make your spin direction is all the same, okay? So then we obtain this modified Hamiltonian. So kinetic term appears the same, impurity term is modified but not interestingly, and the Rashba term disappears. So it is merged into this M prime, and because I rotate my M at every atomic site, then from this rotation matrix I can define chiral derivative. So the special derivative of M in the presence of the Rashba Hamiltonian actually include normal derivative that really measures the spatial derivative of your magnetization, but you have a Rashba correction, okay? That is proportional to the Rashba constant. What is the consequence of this? For example, you can put this chiral derivative to normal derivative in any case, if you have interface. But you always have interface of the surface, so it is very ubiquitous. So one very important energy term that includes this normal derivative is exchange interaction. We have 2 normal derivatives. So now I'm interested in what happens to this exchange energy at the interface. So I replace normal derivative with chiral derivative, and I have original term and the correction term. This correction term comes from the Rashba contribution that is given by y dot m cross gradient n. This is nothing but the Jalosevsky-Moria interaction at the interface. So actually, Jalosevsky-Moria interaction consists of very local physics and non-local physics, and this term describes the non-local physics based on the persistent spin current. Okay, why we have DMI related to the Rashba spin-orbit coupling? So DMI is the energy term, meaning that it must be independent of the current. In other words, there are some contribution for the plus k state, and there may be also contribution from the minus k state. If they are exactly cancelled out, there is no such energy term. So if we have the DMI, which means that this summation of these 2 contributions must be non-zero. And interesting point of the Rashba spin-orbit coupling is that it acts like an effective magnetic field aligned along the k cross z direction. Okay. So, for example, my k is in the x direction and positive, and then this field is pointing out of the slide. Then my conduction electron spin tends to rotate around this effective magnetic field originating from the Rashba spin-orbit coupling and go there in the space. But I have also considered the minus k case. So interesting point here is that if you reverse the sign of k, your effective field changes its sign. Okay? So now let me start from here and go there. And it rotates in the opposite direction, but the propagation direction is opposite, so you have exactly the same pattern. So we have to add up these 2 in order to find out if this mechanism causes some correction to the energy. Yes, it does. conduction electron spin has well-defined chirality at the interface, and you have SD exchange. So your local magnetization tends to follow the itinerant electron spin if the situation is allowed. In other words, you have a magnetization which is chiral, okay, satisfying the DMI. Also, in dynamics, you have a spin motive force. This is more general concept of spin pumping. So, in the absence of the Rashomon spin-Obi coupling, it is well known that there is a spin-dependent electric field, plus minus means up and down spin, that is proportional to the time derivative and space derivative. Oh, I have a space derivative, so I can replace it with a chiral derivative in order to find out what the Rashba correction is. Then I obtain this complicated term, but it can be mathematically simplified like this. So you have additional spin-dependent electric field where inversion symmetry direction Z is very important. Okay. And this is the spin-dependent electric field. Charge cannot see that, only spin can see that. But if you have magnetization dynamics, you have the spin motive force, but this system is ferromagnet, so there is imbalance between the up and down spin. So the spin-dependent response are not cancelled out. So finally, you have charge current. And this charge current within the ferromagnet gives the feedback torque, which is the spin torque. And this feedback mechanism must generate additional damping. If not, that is unphysical. So we can calculate what is the additional damping because of this chiral term. And some equations, and for single domain, now this actually damping, we usually use that is the constant, but that is not constant. This is a 3x3 tensor. And because we use constant because all diagonal components are all zero and all diagonal components are the same, then you can just replace it by a single number scalar value. But when you have the Rashba, then Z component is different from XX and YY because the inversion symmetry breaking direction is special. So you have anisotropic damping. In the domain wall, it's more complicated tensor, so I just take the alpha YY, then you obtain first order fraction, alpha L term in this form. Here phi is dominal angle. So damping can change depending on the dominal angle, meaning that you have a chiral damping. Okay? Okay, then let me move on to the orbital Hall effect. So from my point of view, I was interested in the orbital physics to better understand the spin-Obi torque. And in this paper, they have used a very simple model Hamiltonian, and we are interested in the spin torque, so we have to calculate the spin dynamics using the Heisenberg equation. So kinetic term gives the divergence of spin current Js, and SD exchange gives the spin torque, and L dot S, spin-Obi coupling gives the L cross S torque. When we ignore the spin-Obi coupling, this term doesn't exist, and the spin dynamics is much faster than the magnetization dynamics, meaning that you assume my magnetization is in the steady state, and solve this equation for the steady state. So dSdt is 0, meaning that spin torque is simply given by minus divergence of the spin current, which is nothing but the difference between the injected spin current to the ferromagnet and outgoing spin current from the ferromagnet. So that is well described by the spin angular momentum conservation. So spin angular momentum change of conduction electron spin goes to the local magnetization. However, when we have spin-Obi coupling, spin angular momentum is not conserved anymore because we have additional angular momentum carrier, orbital angular momentum L. Then we need to also calculate the LDT. So kinetic term gives the divergence of the orbital current. And this is the spin-independent electric potential, which is the crystal field. And orbital couples to the crystal field directly. In this paper, they call it lattice torque, and there is L dot S, L cross S. So what really happens for the spin-Obi torque is that when you apply the electric field, you have orbital angular momentum from this torque. And this non-equilibrium orbital angular momentum goes there and generate non-equilibrium spin density through the spin-orbit coupling. And this non-equilibrium spin density goes there and exert a torque to the magnetization. So this is the flow of the angular momentum. Okay? And the orbital Hall effect actually describes this process. What happens when you apply the electric field to the system in terms of the orbital current? Theoretically, the first prediction was done in 2005 for P-type silicon, but forgotten. I don't know why. And then 4 years later, a Japanese group published a very nice paper about the SD tight binding model. It's indeed very nice, but I don't know why, but it couldn't get attention from the community. And 10 years later, Korean group actually say the same thing, but much intuitive way. Then people started to have some interest about this. Okay, as I promised, I will explain orbital texture in the momentum space. As you know, something texture in the momentum space means that something is k-dependent. So concerning the spin texture, we know that there is the spin-Rashba texture in the inversion symmetric broken system. And these are really vectors, they are spin angular momentum. Okay? However, in the central symmetric system, there is no spin texture because there is no direct spin momentum coupling. You know that the electric field couples to K, not to spin directly. So if there is no SK coupling, there is no spin response. So then the question arises, the famous heavy metals, which is known to generate a large spinor effect, is platinum, tungsten, tantalum, and so on. They are all central symmetric materials, but they don't have spin texture. Then why they generate so strong spin Hall effect? It's because of the orbital texture. As I explained before, orbital Rashba comes first in the inversion symmetric braking system, then spin-orbit coupling makes some spin Rashba texture. But in case of the central symmetric system, we have some orbital texture, but here I didn't use vector, something else. So vector means angular momentum. This is different one. And this is orbital angular position. So in my talk, if I say about the orbital texture, it means that orbital angular position, OAP texture, not OAM texture. Then I have to explain what OAP is. Orbital angular position is nothing but a linear combination of real orbitals. For example, in the p orbital system, they are just linear combination of px, py, pz. For example, in this figure, I have a AP orbital state, which has some tilting from the x-axis. Then this orbital p state can be described by the linear combination of px and py with the tilting angle phi. Then I can calculate what is the expectation value of OAM. It must be 0 because it doesn't have any phase difference between these two. But if we use this anti-commutator, second order of L, which is called OAP operator, that measures this tilting angle. Okay? So this is the OAP. If my OAP has some distribution in the momentum space, then I have orbital angular position texture. So actually, orbital angular position texture is present in all solid. Here I use the simplest model, 2D square lattice and p orbital. And we know that hopping, electron hopping from here to there, for p orbital, px orbital is sigma hopping. This is pi hopping. And wave function overlap is different. And therefore, in magnitude, sigma hopping and pi hopping is different. So you have something like anisotropic orbital px band in the K space. However, at every Fermi lattice, you have a same px state, meaning that orbital state does not depend on k. So there is no texture yet. You can do the same thing with py orbital. Now this is sigma hopping, this is pi hopping. So you have this kind of anisotropic orbital band. Again, all orbital state at this red band is py, so there is no orbital angular position texture yet. But now we consider the orbital hybridization. One example is sp hybridization. Here I have a s orbital. Then px to s overlap integral is non-zero, so hopping is allowed. And s to py, this hopping is also allowed, meaning that your px and py are mixed at this moment. Even without multi-orbital system, if you consider next near neighbor hopping from here to there, overlap integral is non-zero, meaning that px and py are now mixed. So now your px and py mixed mostly at this crossing point, and as you know, if there is a mixing or hybridization between two eigenstates, anti-crossing appears. Then you now have two separate orbital bands. Inner band orbital eigenstate follows, this is the tangential direction, and outer band the radial direction. Now orbital eigenstate within one single band is k-dependent, so you have orbital angular position texture. So up to this point, I have not assumed very special thing. 2D square lattice, very boring without any special symmetry, and you see SP hybridization or next neighbor hopping are always there, meaning that OAP texture is always there. Intrinsic orbital Hall effect is actually a consequence of this OAP texture. This is the simplified OAP texture. I apply electric field along the x direction, then this perimeter surface will shift to one direction. So let me focus on this state. It was originally here in the absence of the electric field, and it goes down. But at this k point, the band structure eigenstate is not px, but the linear combination of px and py. So during the time evolution, adiabatic evolution of this orbital eigenstate, this px tends to rotate in order to make it the eigenstate of this orbital state at this k point, meaning that you have counterclockwise rotation of your orbital state. That generates orbital angular momentum plus. Same thing happens here, but now your eigenstate is this direction, so your px orbital tends to rotate clockwise, so you generate orbital angular momentum minus. So in this plot, let me compare input and output. So orbital angular position texture is always there, and I apply electric field, and then I generate plus LZ orbital current moving along the plus y direction, and minus LZ orbital current flowing toward minus y direction. This has the same symmetry with intrinsic spin Hall effect, but there is no spin Hall effect yet because I don't consider spin orbit coupling. Then let me turn on the spin orbit